Hello, my dear friends. Welcome to my YouTube channel. Myself, Dattu Patel, Assistant Professor from LJIT. Earlier lecture, we are already discussed about the eigenvalues, eigenvector, basic properties of eigenvalues and eigenvectors, and example based on properties, and finding the example based on eigenvalues and eigenvectors with the help of eigen characteristic equations, and also discuss about the Cayley-Hamilton theorem. Today's session we are going to discuss about the diagonalization of a matrix. Firstly, what is diagonalization? Let capital A be a square matrix of the order n. The matrix A is said to be diagonalizable if there exists a non-singular, or we can say that invertible matrix capital P such that P inverse AP equal to capital D, where D indicated by the diagonal matrix and capital P indicated by the model matrix. An n cross n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Firstly, we have to find the diagonalizable or diagonal matrix. Then firstly we have to find eigenvalues, eigenvectors. Then with the help of eigenvectors we can go for the diagonal matrix. Let's see the working rule for the diagonalization of the square matrix capital A. First one is finding the eigenvalues of the square matrix A. Here our question which is in form of square matrix 2 cross 2, 3 cross 3, 4 cross 4, etc. Second one is finding the eigenvectors corresponding to the eigenvalues. That means we have to finding the eigenvalues with the help of Cramer rule or a row echelon form as you like. Third one is finding the model matrix capital P by writing the eigenvectors in its column vectors. Fourth one is find the P inverse, and for that P inverse AP equal to capital D, where D indicated by the diagonal matrix. It has the eigenvalues as its diagonal elements. Let's see one example. Find a matrix capital P that diagonalize capital A and determine P inverse AP, where capital A equal to 2 0 minus 2 0 3 0 0 0 3. Here firstly whatever the matrix which is given, that is 2 0 minus 2 0 3 0 0 0 3. Here our diagonal elements 2 3 3, and above the diagonal elements we have the non-zero value, but below the diagonal elements we have the zero value. That means our matrix which is in form of triangular form. That means whenever the below entry of the diagonal elements are 0, then it is called the upper triangular form, or above entries of the leading elements or diagonal elements are 0, then we can say that it is lower triangular matrix. If our matrix which is upper triangular or lower triangular matrices, then its eigenvalue will be elements of the principal diagonal elements. Then here eigenvalues of the matrix A are 2 3 3. Suppose we don't know the properties of eigenvalues, then we can find the eigenvalues with the help of characteristic equations, which is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0, and finding the values of s1 s2 s3 and substitute it in this equation and factorize that term with the help of remainder theorem or a term adjustment method or a division method, and we can find the eigenvalues which is also same as, that is 2 3 3. Now with the help of eigenvalues we can find the corresponding to the eigenvectors. Now we will find the eigenvectors corresponding to these eigenvalues. Let's see for the lambda equal to 2, then here a minus lambda I into x equal to 0. Then our matrices becomes 0 0 minus 2 0 1 0 0 0 1 in column matrix xyz equal to in column matrix 0 0 0. In this equation we written in form of system of linear equation, that is minus 2z equal to 0, y equal to 0 and z equal to 0. Among these equations we have to finding the values of x, y and z. Here we have the, suppose say x equal to t1, where t1 belongs to R and T is equal to T1 is equal to any arbitrary constant. Then capital X equal to substituting these values of X, Y, Z in a column form. Then T1 0 0 here T1 which is common out. Then T1 into 1 0 0 is equal to T1 into X1, where X1 is a linearly independent eigenvector corresponding to the eigenvalue is 2. Similarly for the lambda equal to 3, here we have the eigenvalue which is 233, means 3 which is repeated. If we have the eigenvalues in form of non-repeated form, then we apply the Cramer rule. Suppose we have the eigenvalues which is repeated form, then we use the row echelon form or a reduced row echelon form. Here 3 which is repeated, then with the help of row echelon form, we can find the eigenvector. Here characteristic equation of the a minus lambda into x equal to 0, that will give you minus 1 0 minus 2 0 0 0 0 0 0 in column form x y z is equal to 0 0 0. Then our augmented matrix is minus 1 0 minus 2 0 0 0 0 0 0 oblique 0 0 0. Here we have the leading element only first row. In second and third row are the leading was not present. Means second and third row, each and every elements of the second and third row are 0. That means our x variable was present, but x2 and x3 was not present. That means at position of x2 and x3 or a y and z position, leading was absent. That means y and z are the free variables. Means assign another variables at position y equal to t2 and z equal to t3. That means where t2 and t3 are the arbitrary constant which is belongs to R. Now among this above equation, we have to find the system of linear equation which is minus x minus 2z equal to 0. That means minus which is common out, that will give you x plus 2z equal to 0. We already assigned the variables y and z which is substituted in this equation, and finding the values of x, that will give you x equal to minus 2z equal to minus 2t3. Here we have total two unknowns, t2 and t3. Now substituting these values of x, y, z in our column vector, then capital X equal to x, y, z is equal to minus 2t3 t2 into t3. Now common out the t2, means whatever the term which is multiplied with t2 and whatever the term which is multiplied with t3 which is separating. That means in first column we written in form of t2, in second column we written in form of t3. That will give you 0 t2 0 plus minus 2 t3 0 1. Now common the t2 in first column, that is t2 into 0 1 0 plus t3 into minus 2 0 1 is equal to t2 into x2 plus t3 into x3, where t1, t2 and t3 are the arbitrary constant and x2 and x3 are the eigenvectors corresponding to the lambda 3, which is linearly independent eigenvectors. We have the total 3 eigenvectors. Now we have to finding the model matrix P, that it has eigenvectors as it in its column vector. Means P equal to eigenvectors for the lambda equal to 2, then eigenvectors for the lambda equal to 3, that is x2 and x3, which is written in form of column. Then p equal to 1 0 0, that is eigenvector of the for the lambda equal to 2, and 0 1 0, that is and minus 2 0 1, that is eigenvectors for the lambda equal to 3. That is our model matrix P. Now we have to finding the P inverse. For that, here we apply the Gauss-Jordan method. Basically, there are the various methods of finding the inverse with the help of Cayley-Hamilton theorem, with the help of Gauss-Jordan method, with the help of determinant method. Determinant method, which is already you learn in 12th science, which is P inverse equal to adjacent of P upon determinant of P. You can any method apply to finding the P inverse. Here I apply the Gauss-Jordan method. For that, P equal to I3 into P. There I3 indicated by the identity matrix. Now substituting these values of I3 and P, that is 1 0 minus 2 0 1 0 0 0 1 equal to 1 0 0 0 1 0 0 0 1 into P. Here whatever the value in form of P means that is our LHS portion. We have to making the identity matrix of the LHS portion. For that applying the only row operation. Whatever the applying the row operation for the RHS portion for making the P to the identity matrix, that is automatically applicable for the identity matrix. And at last stage, we apply whenever the our matrix P become the identity matrix. At that position, RHS portion also change, means identity matrix becomes in another matrix, that is B. That is B equal to P inverse. That is our values of P inverse, which is already learned in earlier lecture. Let's see first row operation, that is R1 plus 2R3. That will give you 1 0 0 0 1 0 0 0 1 equal to 1 0 2 0 1 0 0 0 1 into P. Now that is our identity matrix. Then P inverse equal to 1 0 2 0 1 0 0 0 1. That means I3 equal to P inverse into P, where P inverse equal to 1 0 2 0 1 0 0 0 1. Now for the finding the diagonalization or a diagonal matrix, that is P inverse AP. Now substituting these values of P inverse A into P, then P inverse, that is 1 0 2 0 1 0 0 0 1 2 0 minus 2 0 3 0 0 0 3 1 0 minus 2 0 1 0 0 0 1. Now multiplying this means first we multiplying P inverse into A, and whatever the answer of the P inverse into A, we just multiply with again P and simplified it. That will give you 2 0 0 0 3 0 0 0 3. That is our diagonal matrix. Diagonal matrix means we have the only diagonal elements except this. Remaining all these values are 0. Here our diagonal elements are 2 3 3. That is exactly our identity matrix. Means no need to multiply it or simplify it. We can put directly eigen values 2 3 3. Here whenever we solve the examples of the diagonalization, then we consider the first we consider the model matrix P as an eigenvector for the eigenvalue 2, that is 1 0 0, for the eigenvector 3, for the eigenvector of the eigenvalue 3, that is 0 1 0 and 2 0 3. For that we have to put the eigenvalues in diagonal elements, that is 2 3 3. This is all about the required diagonal matrix, which is 2 0 0 0 3 0 0 0 3. This is all about the topics of the diagonalization. I hope you guys learn something from this video. If you like this video, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorial like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. If you have any query regarding this, then feel free contact me. Thank you so much for watching me.